Okay. Sorry about the delay. Right, so let's start by remembering where we were when we left off. So our goal was basically to prove that, to prove that the endomorphisms of this coherent Springer sheaf were isomorphic to the affine Hecke algebra as a DG algebra. And as we saw last time, that would actually prove on a categorical local Langlands correspondence for the Iwahori block in the setting we were working in. So we wanted to do this, and we basically replaced these things with versions where Q was replaced by a parameter that was allowed to vary. So it suffices to show that instead that end of S1 GT was isomorphic to this HF GT, where S1 GT was P lower star of O par 1B T along the map from par 1B T to par 1 GT. And we hadn't yet shown this, but we had identified, this T version of the affine Hecke algebra, HF GT, as a DG algebra with the Hochschild homology of what I'll call STG prime, where since there have been a lot of Steinberg varieties and variations on them seen today, let me just remind you that this is equal to the nilpotent cone of B mod B prime, whole thing crossed over nilpotent cone of G. Sorry, there should be hats on everything here. Of G hat mod G hat prime with itself. And then at the end of the last lecture, we'd identified a link between the spaces appearing in the definition of this Steinberg scheme and or Steinberg stack and the stacks of parameters. So we had this loop space construction defined by Lx is x crossed over x cross x with x, this derived self-intersection of the diagonal in a stacky sense. And what we had seen was that the loop space in particular of ng hat, I should say here, g hat prime was g hat crossed with an extra copy of gm. That was where this parameter t that we had thrown in was coming from. And then what we had seen was that the loop space of this ng hat mod g hat prime was isomorphic to par 1 gt. And similarly, if I replace g hat with b hat here, then I get par 1 bt. And if I do the Steinberg loop space of the Steinberg stg hat prime, this is par 1 bt crossed over par 1 gt with par 1 bt. Okay, so that was as far as we'd gotten. And what I want to do today is basically use these observations to conclude the argument. And the basic slogan is that when you have a stack with a convolution structure like STG hat, then its Hochschild homology can be related to endomorphisms of objects in the categorical trace of the category of incoherent sheaves on that. So our next step is to relate this to categorical traces. Let me fix some notation, since we have multiple categorical traces to think about in this picture. So let me first talk about the one categorical trace. So if I have A, one of these monoids in presentable stable infinity categories, so all of these will be categories of coherent sheaves in our picture with some kind of convolution structure on them, then HH of A, which I guess we've also seen called lowercase trace of A, is given by this, so this is an algebra in vect of QL bar. All of our categories are QL bar linear, and it's given by basically looking at the composition of the co-evaluation from vect QL bar to A tensored over A tensor A rev with A, and then evaluation back down to vect QL bar. So if you look at one in here, that gives us an object of vect QL bar that we call HH of A, and so the a priori, that's just a complex, but the monoidal structure on A gives it the structure of an algebra object, a DG algebra in this context. And then, I should say, because all of the traces we're going to be taking here are traces with Frobenius, traces of Frobenius, but because we're in the split setting, Frobenius is just acting via the identity on the spectral side. So these are all categorical traces of the identity, and I'm just going to drop the endomorphism from the notation here. So if you're trying to reconcile this with Arnold's talk, just put in the identity everywhere. And then we have a kind of grown-up version of this, the two categorical trace. And this doesn't take as input A, it takes instead the two category of module categories over A, and it gives us back out some presentable stable infinity category, and this is given by A maps to A tensor over A tensor A rev A. And there is a natural sort of Chen character in this setting, which I'm going to denote by brackets, takes a module category over A, and it returns an object of trace of A mod, one of these objects here. Okay, and the point is that these are related in the sense that lowercase trace of A, which is just different notation for the Hochschild homology of A, is the endomorphisms of the endomorphisms in the categorical trace of A mod of the regular representation of the image of A itself considered as a module over A under this bracket operation. Okay, so that's some notation. Okay. Sorry, trace of A mod is, yes, this is an object of PR.
The thing next
Yes. Yes. So sorry about that. This should be an object of PR.
Perhaps capital trace of a mod is modules over what you wrote.
No, A is a category here.
A is a category. Oh, yes.
Yes. Yeah, so A mod is a 2 category. Okay. So right. So we're going to be applying this in a specific framework. So that's motivated by this picture up here. In particular, we're going to be interested in the categorical trace of incoherent sheaves on this Steinberg stack, STG hat prime up there, because that's our stack with convolution structure, and so incoherent sheaves on it will naturally be one of these objects. But I want to set things up in a bit more of an abstract framework because the principles we're using here are very general. And so in a lot of the motivating source material for this, one deals with, one looks at a map between a self-fiber product coming from a map between, say, smooth Artin stacks or something like that. But unfortunately, this nilpotent cone of G hat mod G hat is not smooth. So we need some better hypotheses than that. We need some weaker hypotheses in particular. And so let's take f from x to y proper. That's harmless for us. Surjective. And then we want this extra kind of vaguely like a smoothness condition, which just says that the relevant cotangent complex is perfect and concentrated in degrees 0 and 1. I think these are homological degrees, incidentally. Normally, for most of this, I'll be using cohomological grading, but I think this statement is homological in nature. Okay, so we have this, and we'll take z is equal to x cross over yx, and the motivation you should have in mind here is that x is nb hat, mod b hat prime, and y is ng hat, mod g hat prime, so that z is st g hat prime. Okay, so what we saw in Arnaud's talk, and which doesn't quite fit into the framework here, is that in the case of affine schemes, we've seen that. So if z is affine, we've seen that the Hochschild homology of Q-co of z was equal to functions on the loop space. And the point is that, so the point is that LZ here is LX crossed over LY LX. The loop space construction commutes in this way because you're basically just playing games with fiber products. And the point is that in nice situations, so the point is that in a lot of generality, one has that end of, let's say, LF star OLX. Well, this looks like Hom. So this is end LY, but you can rewrite that as Hom LX of OLX with LF upper shriek, LF lower star, OX. And in turn, because we have a Cartesian diagram, you can rewrite this as Helm LX, OLX, LF tilde lower star, LF prime upper shriek, OX, where here we're looking at the diagram LX crossover LY, LX to LX to LX to LY. So we have LF, LF, LF tilde 1, LF tilde 2. OLX, yes, thank you. And then we can just pull this back, and this becomes let me say LZ. So Z is this guy, remember, or LZ is this guy. So this is OLZ, LF. Sorry, there should be a tilde here. LF tilde upper shriek, OLX. And the point is that in nice situations, including ours, so in many situations, OLX is isomorphic to the dualizing sheaf on X. And in that case, this just becomes and OLZ is the dualizing sheaf on LZ. And so in many situations, this just becomes R gamma LZ of OLZ and is therefore the Hochschild homology because of sorry, where did I write that? Yeah, so the Hochschild homology was, how did this? Okay, yeah, we had that the Hochschild homology was, that's the wrong one, was R gamma LZ, OLZ, and now we've identified that with the endomorphisms of LF star OX, which in our setting is the Springer sheaf. So in this if we were dealing with affine schemes, we could just argue like this, but instead we're going to have to work a little harder. In particular, an issue is that we're not working with QCO, but we're working with INDCO. And in the smooth world, that wouldn't matter, but it does matter for us. And so instead, we're going to have to appeal to this hard result of Ben-Zvi, Nadler, and Pragal in 17. And actually, we need a little more because they had some smoothness hypothesis that turns out to be superfluous, but that certainly doesn't hold in our setting. So what they actually show is that if you take this two categorical trace of INCO of Z modules, then what you get is incoherent sheaves on Ly with a certain singular support condition. So I'm not going to explain exactly what this lambda is. I'll just say that this is a singular support condition. And the reason I'm not going to explain what it is because miraculously, in the situation we're working in, that condition turns out to be vacuous. And moreover, what they show is that this bracket applied to inco z as an inco z module, well, that should be an object of inco ly. And what object is it? Well, it turns out it's exactly LF star OX. And that implies, in turn, that the Hochschild homology of inco z, remember the Hochschild homology is this little trace, and we had seen that the Hochschild homology was the Hochschild homology of the regular representation of the monoidal, the regular representation of a monoidal category is the endomorphisms as a DG algebra of the trace of this, of its trace, of its two categorical trace. So that actually ends up being this. And I'm still not done with the statement of the theorem. The last thing they show is that the standard representation, in other words, you can consider inco of y as an inco of z module via this convolution action. And the trace of that just turns out to be OLY. Inco of x. You don't have a convolution structure on y. You don't have a convolution structure on y, but you do have a convolution structure on inco of x, and its categorical trace is OLY. Okay, so let's apply this with x's and b hat, mod b hat prime, and y is n g hat, mod g hat prime. And you see that what this is saying is that the categorical trace of inco Steinberg, I guess I should say first, the trace of inco Steinberg is exactly inco of par 1G. As I said, technically one needs a lambda here, and if we were working with modular coefficients, that would matter, but in our case, it turns out it doesn't. Moreover, trace of inco of Steinberg is the push forward from Lx to Ly. That's the push forward of the structure sheaf. Sorry, this should be OLX. And that's exactly what we called the Steinberg variety, the Springer sheaf S1 GT. And so this tells us that HH of inco of Steinberg is end of S1 GT. But we'd already seen that this was isomorphic to the affine Hecke algebra HF GT, so we've won. Well, we haven't quite won because we have to check compatibility of our construction with parabolic induction, and we have to check its compatibility with the Whittaker function. But compatibility with parabolic induction at this point is something you can check on the level of H0s, right? Once you know that all of your DG algebras are concentrated in degree 0, you can then maps between them are the same as maps on their 0th cohomology, and that turns it into a question on K-theory. If you remember going all the way back, ultimately this map comes from the Kazhdan-Lusztig identification of the Hecke algebra with K0, and that has a natural compatibility with parabolic induction built into it. So compatibility with parabolic induction is fairly easy. And then the other thing we needed to check is that it takes the Whittaker functions to the structure sheaf on par 1G. And in terms of Hecke modules, that means that what we need to check is that when we think of this space of Whittaker functions as a Hecke module, that's the same thing as thinking of OLY as on the other side of the categorical correspondence we've built. That's the same thing as thinking of Helm S1G OLY as an end S1G module. And so one has to check that those things are the same, but what one uses is that this module category, this OLY that we're trying to hit, is the module category of this in co-X, the standard representation of co-Z, and that's a categorification of the sort of standard representation of the Hecke algebra, what's called the anti-spherical representation of the Hecke algebra. So compatibility with Whittaker data comes ultimately from the fact that that if you look at K0 of X of NB hat mod B hat as a K0 mod B hat prime as a K0 of STG prime module, this is the anti-spherical Hecke module. And so after passing through first Hochschild homology and then this categorical trace construction, that tells us that, that OLY considered as a module over end of the Springer sheaf is the anti-spherical Hecke module, and therefore these two things match up. Okay, so that completes the proof of our theorem, at least on the Iwahori block. Let me stop here and ask if there are questions before we go on, and then I'll spend probably the rest of the talk doing an extended example. Okay, if there are no questions, then I want to switch gears quite a bit and drop all this abstraction and stress that, one question. How do you get par 1G? So par 1G in this picture is the loop space of Y, right? It's Ly. Yeah, so this is, yeah. Okay, yeah, so the Steinberg is always LZ, Ly is par 1G, Lx is par 1B. Okay, so now I'd like to switch gears and talk a lot about GL2, because in spite of all the abstraction we used to prove this theorem, what I want to stress is that the results are actually, once you have this result in hand, it's actually very, very nice to compute with, and you can make a lot of things very concrete. So from now on, G is GL2, and I want to draw, and we still have T sitting inside B, sitting inside G, and I want to draw the various moduli spaces of parameters that are involved in spectral parabolic induction in this case. So I'm going to draw par 1T as a vertical line like this. So a typical point here, I'm just going to think of as a diagonal matrix, A1, A2. And remember that I'm modding out by the action of T here. Okay, so par 1B is a little bit harder to draw, but what I'm going to do is I'm going to allow myself to diagonalize Frobenius. And so when I do that, if I look at par 1B, yeah, sorry, I shouldn't say par 1T mod T here. What I mean is that I have this copy of the torus, and it's acting on itself. It's acting on itself by conjugation. So par 1b looks very similar. If I diagonalize my Frobenius, then for the most part, I have an action of the torus here that's largely trivial, but now at the identity, let's call that point the identity, I have an extra little action. The identity has some extra automorphisms given by B. But then I have an extra component because a Langlands parameter also carries this factor n, and for this n to be non-trivial, Frobenius has to conjugate it to q times itself, which means that its eigenvalues have to differ by a factor of q. So these are the points of the form, let's say p, a, and then an n of the form 1 star 1. And this still has an action of t. This still has an action of t on it, but now t can move the monodromy operator around. It can change the value of this star. So t kind of expands. The action of t kind of expands and contracts this component, and only fixes its intersection with the unramified component.
Do you have ones or zeros in the diagram?
Oh, yes. Okay. And then I'm going to draw par 1g, and it's going to look exactly the same, except there are going to be two slight changes. First of all, the identity now becomes a bit bigger. Actually, the identity was always a bit bigger. So these are unipotent matrices now. Well, yeah. What do I want to say? I want to say. What do I want to say? So there are 2 points here. There's the identity with automorphisms g hat, and the non-trivial unipotent with automorphisms b hat, not with automorphisms z hat, u hat, on this kind of weird point. And then up here we still have a component much like the component above, but this projection P behaves differently on the two components. So in particular, the diagonal matrix with entries A and B is not B conjugate to the diagonal matrix with entries B and A, but it is G conjugate. And so on the vertical line, this map is 2 to 1. But on the horizontal line, the map is 1 to 1. So we have a picture that looks like this. And now, so what does the Steinberg, what does the Springer sheaf look like? It looks like the push forward of the structure sheaf on par 1b. And you can see that what's happening is that on this horizontal component, that push forward is just going to give us something of multiplicity 1 because it's 1 to 1 there. And on the other component, it's going to be 2 to 1, except there's something weird going on near the identity, where you've got this unipotent stuff that so you've got unipotent cone of B mod B mapping to unipotent cone of G mod G. That basically has a fiber that looks like a P1 in it. But it turns out when you push forward, essentially because the cohomology of P1 is so simple, that doesn't contribute anything. And so what you really get here is something that's multiplicity 1 along the vertical fiber. along the vertical line and multiplicity 2 along the vertical component and multiplicity 1 along the horizontal component. So this is the structure sheaf of par 1G. You know that has to be involved because of the unit map, but then you get an extra copy of the structure sheaf of the vertical component, which I'll call par G unramified. So this Springer sheaf looks like this. And once you've done this computation, you can start to see lots of interesting things. So there we go. So remember that, why are you not? Okay. Remember that the categorical local Langlands correspondence takes this generator, IB op G of the universal unramified character, to the Springer sheaf. And this parabolic induction has its own natural direct sum decomposition, as we'd expect because we have an equivalence. This is isomorphic to the compact induction from I to G and Iwahori subgroup to G of the trivial character. And that in turn is isomorphic to a parabolic induction from K to G of the trivial character, direct sum, a parabolic induction from K to G of the finite Steinberg representation. So let me write this as ST bar to distinguish it from the Steinberg variety that we wrote down earlier. And well, this induction of the Steinberg representation, this is actually equal to our space of Whittaker functions WU psi. And so we know that that sum end maps to the structure sheaf on par 1G. And so by splitting that off, what we see is that the other sum end, this spherical module in KG1, that maps to this structure sheaf of the unramified component. So this implies that CLLC of in KG1 goes to O par G unramified. So we have these two very nice projective objects in the category of representations of GL2, and under categorical local Langlands, one of them goes to the structure sheaf on the whole thing. That's the space of Whittaker functions. And then the spherical representation goes to the structure sheaf just on this vertical component, par 1G unramified. Incidentally, if you weren't already convinced, this should convince you that we really need to be talking about incoherent sheaves rather than quasi-coherent sheaves. The reason is, if you want to think of this as a piece of a larger equivalence of categories, then it should be carrying compact objects to compact objects. And the space of spherical functions is certainly a compact object. It's a compact induction in degree 0. So it's a finitely generated projective in degree 0. So it should go to a compact object. But in the category of quasi-coherent sheaves, the compact objects are the perfect complexes. And this is not a perfect complex, right? In general, if you have a pair, if you have just the union of the coordinate axes in A2, and you try to resolve the structure sheaf of one of those axes, that resolution has infinite length. Because first you have to multiply by x, and then you have to multiply by y, and then you multiply by x again, et cetera, et cetera. So this is not compact, but it's a perfectly good coherent sheaf. And so the target category needs to be a category in which the coherent sheaves are all compact objects. And that's exactly what the category of incoherent sheaves does for you. So if you understand these examples well enough, you can actually guess at the shape of the conjecture. Okay, so let's now try to compute with these things a bit. So you can build interesting objects now by thinking about these two. So the point is that let's consider maps between these objects. So in fact, you can check that Helm in KG ST bar int kg1, this is free over the Bernstein center, over the center of the affine Hecke algebra of G. And if you choose a map that generates it, that generates this Helm space over the Bernstein center, in kg st bar, so let's choose a map between them that generates it. That map is going to be an injection, and it turns out the kernel of such a map is the universal character of G. So in other words, you take the universal unramified character of Gm, compose it with the determinant, and that turns out to be the co-kernel here. The reason is that these are projectives, and so the co-kernel, and this is a generator for the Helms between them. So the co-kernel consists of all the quotients of the target that can't be written as quotients of the domain. And what are the representations of GL2 that are spherical, that can be written as quotients of in kg1, but can't be written as quotients of in kg Steinberg? They're exactly the characters, the non-generic representations of G in the unramified block. Okay, so that suggests that we should have, if this equivalence were an underived equivalence, then we would expect an exact sequence of the form, we would expect an exact sequence where the first term is the structure sheaf on the whole thing, the second term is the structure sheaf on the unramified component, and then the map between them should generate all of the maps between them, and then that's kind of bad because that kind of looks a little bad at first glance because the structure sheaf of the whole scheme maps surjectively onto the structure sheaf of a subscheme. And so this is a sign that the equivalence has to be derived. So in fact, a derived equivalence doesn't preserve exact sequences, but it does preserve cones. And so you can write down the cone of this map, but it has that cone has cohomology that's not in degree 0. So what happens is that this map from nkg st bar to nkg1 goes to the only thing it can possibly go to, up to multiplication by some unit in the center, say. Namely, we have O par 1g here to O par g un. The structure sheaf of both components mapping to the structure sheaf of one component, and that's surjective. So it maps to 0, but now it has a kernel, and that kernel is the ideal sheaf of par g un, but living in degree -1. And so if you take that cone and form a long exact sequence of homology out of it, of cohomology out of it, it doesn't have terms exclusively in degree 0. It's not a classical exact sequence anymore. Instead, all of these characters, all of these non-generic representations of GM have been pushed up into homological degree -1. And this seems to be a general phenomenon that's kind of mysterious. It seems like the more degenerate representation you put into the categorical of the Langlands correspondence, the lower its cohomological degree, the more negative its cohomological degree gets. And I don't think there's anybody who's managed to systematize that or articulate a sort of precise statement along these lines. But as a rule of thumb, it works very well. And in cases where you can compute things, like in cases where, for instance, Frobenius is regular semi-simple, then this really seems to be true in some very strong sense. So I think there are lots of interesting questions to attack there. Okay. Yeah, maybe I shouldn't put the cohomological degree in here. Instead of saying that, I'll put it. Okay, that looks better. Okay, so this is now happening in degree -1 up. Okay, is there a question?
No, just mumbling, sorry.
Okay.
You say that the more deterrent you are, like the further away from the residual you get pushed?
Yes, it seems that way at least. And
Do you have like numerical predictions for this?
I have some guesses, but not ones I'm willing to share in public, so maybe we should talk in private at some point.
It's not hard to check from the nature of your embedding that like this is t bounded, sort of with amplitude in the interval
Yes.
1 minus n, comma 0.
Yeah, so in fact we'll see in a second that if you look at all the irreducibles in this particular case, they'll actually live in either degree 0 or degree -1, or possibly a mix of the two in one case. And then in general for GLN, you can that live in degrees 0 through negative n plus 1. But I don't know precisely what the statement is for groups beyond GLN. Is it just the rank, maybe?
It should be minus the semi-simple rank.
Minus the semi-simple rank. Yeah, that sounds vaguely plausible.
For quasi-simple.
Right. Okay.
Also, could you say a word about where that sequence is the non-derived one?
Yeah. So I mean, so this is something you can write down basically via Mackey theory, essentially. So if you just take, right, so what does this look like? What does this Helm space look like? It looks like functions from G mod K into Helm ST bar 1 that have some equivariance properties on both sides. And you can compute that, and it turns out it turns out to look exactly like a free module over, say, the spherical Hecke algebra. And then to get this, to figure out what the co-kernel of a map between them is, you ask basically, well, you use the fact that both these things are projective, and therefore the Helm. The image of all the Helms together, which is the same as the image of a generator for the Helm space, kills everything except for quotients of the target that are not quotients of the source. And so you look at the biggest quotient of this spherical thing that's not a quotient of the source, and that's what gives you this. That's what gives you all these characters, basically. That's right. Basically everything but the finite dimensional ones.
Wait, one more time. If you scroll up to your picture, R1G, it's a little hard to make out. Is there a point floating there that has to do with a non-Frobenius semi-simple parameter?
Yes. Yes. So in terms of the push forward doesn't actually see any difference between those points and the surrounding points. But that's a calculation you have to do. So what this looks like is there's sort of 2 points. There's the semi-simple point, which looks like the identity or like a scalar, and then there's the non-semi-simple point. And basically that thing looks like a little copy of the unipotent cone of B upstairs or G downstairs, and the map between them is actually a little copy of the Springer resolution. And when you push forward along that, well, all the higher derived push forwards vanish, and you're just left with the same sort of skyscraper sheaf you would have gotten at a point away from that.
It's just a little hard to read. How it fits into the picture? Is it an isolated point?
No, it lives on par 1 unramified, par G unramified or par B unramified, and it's just what you, whenever in par B, if you're degenerating something with a pair of distinct eigenvalues to something with a pair of simultaneous eigenvalues, the closure can contain non-scalar unipotent things. So this really varies continuously in the stacky world with the rest of it. It's just hard to draw it that way because unfortunately, no one has invented stacky paper yet, basically.
It's like the geometry of the vertical part doesn't change there, but like the map to the course moduli has something bigger there.
Yeah, the map to the course moduli is kind of branched there. It's on the vertical part, and it's just this weird kind of point with weird stacky behavior that doesn't seem to have any representation theoretic significance.
And what did you draw next to it? It looks like 2 hat
This is, is this 2 to 1 here? That's just the.
Right? Yeah. In the fourth quadrant.
So there are 2 points. There are 2 points in this fuzzy bit. There's the scalars whose automorphisms are G, and a unipotent orbit where the automorphisms are representative are the center together with the unipotent part. That is a Z. Okay, does that help? Okay, great. Great. So we've seen what some big representations do when we map them around. The other thing to compute is parabolic inductions. So let's take now a character. Let's look at a parabolic induction of a character of a torus. So let's look at I B op G of, let me say, chi A tensor chi B. So what does this look like? Well, this is P lower star of Q upper star of the structure sheaf of the skyscraper sheaf on par 1T at this point AB. So let's go back to our picture and try to see what that does. So in this picture, if I take a point over there and pull back, if I take the skyscraper sheaf of a point over there and pull back along Q, as long as I'm avoiding that horizontal component, that's going to be a flat pullback, and I'm just going to get a skyscraper sheaf again. And then when I push it forward, well, the push forward is 2 to 1, but it's finite most of the time, and therefore I just get a skyscraper sheaf down here. There's this one funny point where if A equals B, then I end up in this fuzzy locus, and then Q still turns out to be flat there. So I get the skyscraper sheaf on this fuzzy locus, which remember that I'm going to think about now as the structure sheaf of the domain of some kind of Springer resolution. And when I map that down, when I push that skyscraper sheaf down, I just get the skyscraper sheaf on the corresponding orbit over here. So almost all of these parabolic inductions are skyscraper sheaves, including a reducible one. So if A2 is equal to Q times A1, then the parabolic induction is reducible. But in spite of that, when I pull back and then push forward, I'm just getting the skyscraper sheaf of a point over here. So there's some funny derived business going on there as well. And in fact, it's easier to see what that funny derived business is when I do the pullback in the other direction. So I get a parabolic induction that's K-theoretically the same, that has the same Jordan-Holder constituents, if I start from the point QA1, A2. That's exactly a point where the pullback runs into this horizontal component, and so the pullback is not flat. When you pull the skyscraper sheaf there back, you get a complex that lives in 2 degrees. It lives in degree -1 and degree 0. You basically write down a resolution of that point, and when you pull it back, well, that point's cut out by 2 equations, and when you pull it back, one of those equations vanishes identically on this horizontal component. So you get Tor in 2 degrees. But then pushing forward is again finite in this case, so it's affine, it's exact. So all of the derived business is happening from the non-flatness of the Q upper star here. And so if you write down what you get in these cases, so I, B, op G, chi A, tensor chi B, this is equal to the skyscraper sheaf on par 1 G with coefficients AB, unless A is equal to QB, and it's equal to, if you work it out, it's
So you also have to rule out A equals B.
no, it's still equal to that in the case A equals B. What is going on here? Stop that. I don't.
In that case, doesn't it live on the whole fiber of the map to the force moduli? This copy of the unipotent derived?
I have no idea what this software is doing. Oh, yes, you're right. It's not. Sorry, let me say what I mean by this locus par GAB. I mean the locus where the semi-simplification of Frobenius is conjugate to. Okay. Let me just stick that in. Okay. What is going on here? Okay. Sorry about that. Right. So here, par 1G AB, this is Fn such that F is G conjugate to diagonal AB. And otherwise, it's this 2-term complex. It's O par 1B of let's say QBB. So remember that this includes in degree 0, and it's the ideal sheaf inside par 1B QBB of, let me say, par B unramified QBB in cohomological degree -1. So that's a bit of a mess, but this actually dovetails very well with what we know about reducibility of parabolic inductions. So do I have time to do this? I just need about another minute. So in particular, we have 2 exact sequences. 0 goes to 1, goes to I, B op, G, delta to the 1/2, goes to the Steinberg representation, goes to 0, and 0 goes to Steinberg, goes to I, B op, G, delta to the -1/2, goes to 1, goes to 0. And this one goes to the skyscraper sheaf. This one goes to some crazy complex. But if you look at what's going on in terms of the picture, so if you look at these things on G, on par 1G, the parabolic induction in one order lives at this intersection point. The parabolic induction in the other order is some crazy complex, but it's basically the fiber in degree 0 and then the ideal sheaf of that intersection point in degree -1. So K-theoretically, that's the same as the point, right? If you subtract a scheme from the ideal sheaf of a smaller scheme inside of it, you just get the smaller scheme inside of it. So these are K-theoretically the same. And what's going on is, well, we already saw that characters live naturally in degree -1. So the character part of this is living in homological degree -1. And in one direction, you get the Steinberg representation, which is the structure sheaf of the whole component, mapping to the parabolic induction, which is a point, and that's a surjection. So the quotient in the representation theoretic world becomes a sub instead in homological degree -1, and that's the sum character. In the other direction, you genuinely get a sequence in degree 0. In the other direction, you have some crazy complex where the character maps into it, and the Steinberg is what's left over as the kind of cone of that map, basically. So the upshot is that mostly the irreducible parabolic inductions go to structure sheaves. The Steinberg goes to the structure sheaf of an entire fiber along this horizontal component, and then the two parabolic inductions go to the point there and some complex that sort of realizes the point K theoretically, but across two different homological degrees. And I think I'm pretty much out of time, so I'll stop there.